Hello, my name is Adrian Sampson, and this talk is about something called probabilistic assertions, a new way of expressing correctness for programs that don't behave the same way on every single execution. My co-authors on this work are Pavel Pachenka, who's another grad student at the University of Washington, as well as Todd Mikwitz and Catherine McKinley, my co-authors at Microsoft Research, and my advisors, Dan Grossman and Luis Ceza. The key takeaway from this talk is that probabilistic assertions are a new way of expressing correctness properties for important classes of software that isn't deterministic, and that we have a new verification strategy that can check these assertions both efficiently and accurately. But before we get to probabilistic assertions, I want to talk for a little while about our old friend, the traditional assertion. Assertions are great because they help specify little snippets of programmer intent, what it means to be correct for a program at a given point during execution. We like them because we can use them for testing, for static verification, or for runtime checking. But let's be clear about what an assertion means. If a programmer writes assert E, they're saying that the expression E must be true on every single execution of the program that reaches that point of the assertion in the program. And I argue that traditional assertions are simply insufficient for expressing correctness for a large class of programs where that is just too restrictive. One of the most important classes that I'm concerned about is in approximate computing, where the idea is that we can build computers that can be much more efficient if they're allowed to make mistakes some of the time. And those errors are often non-deterministic, meaning that programs can execute incorrectly some of the time in order to gain back a lot in terms of energy efficiency or performance. This means that writing down an assertion that has to hold in every execution is insufficient. We need to allow occasional errors, but still constrain the correctness of the program. The same is true of not just approximate computing, but other domains, like when in mobile applications that use sensors. Sensors have error, as well as when you're obfuscating data for privacy using random noise. The common thread between these applications is that traditional assertions are insufficient. Because these programs don't behave the same on every execution of the program, the assertions that capture their correctness have to be tolerant to that fact, and traditional assertions are not. Let's do an example from that domain of obfuscating data for privacy-preserving computation. In this example, we are, say, Glassdoor, and we want to compute the average salary for a bunch of employees without knowing the precise salary for any of those particular employees. So the strategy is to take the salaries for all of the people that we're surveying and add a random distribution to those salaries before computing the average. And it can be shown this preserves the privacy of each individual, but we need to be able to check that this average is still useful in some sense. So we might want to write down an assertion that says that the different distance between the true average, the unobfuscated average, and the average of the obfuscated values is not too large. Say it's less than $10,000. But the way this assertion is currently written, using a traditional assertion, is just wrong. This is not true on every execution of this program. Because we're adding random noise, part of the power of obfuscation is that we can add arbitrarily large noise during some executions. And this means that even though we want to express this property, saying that it must be true on every execution is false. So what we need is not a traditional assertion. What we need is a variant called a probabilistic assertion. In a probabilistic assertion, or a p-assert as I'll call it, the programmer gives you an expression E that they want to be true at least probability p, meaning that at least a fraction p of the time, that expression is true for a given execution. And because this is necessarily a statistical construct, the programmer also needs to give us a confidence level c at which we'll do the verification. I hope you're convinced that probabilistic assertions can capture properties of programs that traditional assertions can't, and that now you'll put them in all the applications that you write in the future that run on mobile phones, say. But you may be wondering, of course, what are we going to do with these assertions? Now that we have a probabilistic assertion, how can we actually verify it? There is one very straightforward, naive way to verify a probabilistic assertion. We can just take our program and execute it lots of times, for some definition of lots, hundreds, thousands, millions of times. We'll execute the program, count the number of times the expression E is true, and then compare that with the probability P requested by the programmer. There are two obvious problems with this approach. The first is accuracy. How do we know that we have executed the program enough times that we have met the obligation to statistically prove up to a confidence level C that the assertion is true with probability P? The second is efficiency. By executing exactly the same program many, many times, we're executing lots of the same code that is redundant, especially when there's parts of the program that behave deterministically. All we really care about is the probabilistic behavior of the program. Instead, I want to turn to another domain of programming languages research that has looked into statistical behavior of programs, and that's reasoning about statistical models. In particular, I'm interested in recent work on probabilistic programming, which has taken probabilistic models expressed in something that looks like a programming language to execute queries and to do statistical inference over those models. In order to verify probabilistic assertions, our goal is to scale up these ideas from statistical reasoning to real programs, and from small hand-tuned machine learning models, for example, up to real software with millions of lines of code. And that's what p-assert verification is about, and that's what the rest of this talk will discuss. And there are 3 steps in our workflow to verifying probabilistic assertions. The first we call distribution extraction, and that translates from the original program, from imperative code, into a representation of the probability distribution that the program will compute. And that happens to be a Bayesian network. The idea behind translating from the program to this representation of a probability distribution called the Bayesian network is that we can now do optimizations on that representation that work like traditional optimizations in an IR and in a traditional compiler. Then we can take that intermediate representation and do verification on this reduced, optimized Bayesian network representing the program. These are the 3 stages in the rest of this talk, and I'm also going to talk at the end about an implementation of this entire workflow for C and C++ programs using LLVM. The first step, though, is distribution extraction. Distribution extraction uses a symbolic execution approach. But unlike traditional symbolic execution, where the inputs to the program are taken as symbolic rather than concrete, we're going to run the program with concrete numbers as inputs, and instead introduce symbols at every point where the program makes a random draw. Here, there's a call to a Gaussian distribution function, where in the symbolic semantics, instead of taking a sample from the Gaussian distribution, we'll introduce a symbol that indicates the Gaussian distribution that will be sampled over. The idea is that we want to give 2 separate semantics to probabilistic programs in our model. The first is the traditional semantics, the non-deterministic execution that makes random draws during execution, and now a new deterministic symbolic semantics that produces an expression DAG that captures all the randomness in the program. And we've shown in our paper that we've proven equivalence between these 2 semantics, meaning that if you execute the original program non-deterministically and you execute that program through symbolic execution and then execute the resulting expression DAG, you get the same outputs. Let's see how that works. In order to construct these expression DAGs, I'm going to show you a little program that has a particular concrete input, and here it's making a random draw from a Gaussian distribution. Both of those are introduced as symbols. That concrete input is just a point distribution, a point mass distribution indicating the particular value. When we do expressions, we compose them, and we can continue doing this, and it proceeds in a straightforward compositional way. I'm going to straighten out for you this expression here, and you can see that we have created a DAG. It's necessary that this is a DAG so that we can preserve the statistical dependence between the random variables in the program. This also works how you might expect through control flow. Here we have an if conditioned on a random value, and what we do is we deterministically execute both sides of the if and combine the heap updates from both sides after control flow reconverges. So here you can see that we have introduced an expression node for E that's a conditional node that composes the expression, the if side of the update to E, and the else side of the update to E. The procedure finishes once we reach a p-assert, and it outputs the sub-DAG rooted at the expression that flows into the probabilistic assertion. But I want to point out one thing to you now, is that we started out using a concrete value as input, but this is not really essential. You can also imagine starting the program just as easily using an input that is abstract, that is using a random distribution as input. This might work, for example, in a case where you have a notion of what inputs you're likely to see at a runtime, rather than just using a particular input to test over. Why I think this is so interesting is that this means that this technique exists in a sort of trade-off space between what we think of as resembling traditional testing and what we think of as resembling static analysis. If you run with a particular input, we give you a result that reflects the program's behavior on that one input, and that feels like testing. You can also, if you have a notion of the distribution of inputs you'll see at runtime, we can give you conclusions that capture the holistic behavior of the program, and that feels more like static analysis. There's a lot more in the paper, including how we deal with unbounded control flow based on probabilistic values. But what's really important, rather than the construction, is what this produces. We've, through a relatively straightforward symbolic execution, we've produced an expression DAG that captures all the random distributions in the program. What's really surprising to me, though, is that this exact expression DAG happens to be something known in statistics for decades. It happens to be exactly a Bayesian network. A Bayesian network is a representation of a probability distribution that statisticians and machine learning people have been using for a long time. In order to translate from an expression DAG produced by our symbolic execution into a Bayesian network, all you have to do is rotate it 90 degrees and reverse the direction of the arrows. Now that we have a Bayesian network, we can proceed with optimization. And what's great about it is that this Bayesian network captures all the random variables in the program, and the edges capture the dependencies between these random variables. And it means that we can sample it in a single pass. But it also means that we can apply knowledge from statistics as optimizations over this Bayesian network as an intermediate representation. And that's what the next section of the talk is about. We want to take statistical properties that are known about Bayesian networks and known about probability distributions and repurpose them as optimizations on this new intermediate representation that's a Bayesian network. Some of these you may even recognize from high school statistics. If you add together two Gaussian distributions, for example, you get a new Gaussian distribution. If you scale a uniform distribution, you get a new uniform distribution. If you do a less than between a known distribution and a constant, that's just a cumulative distribution function, and we can replace that with a Bernoulli. These are all really basic statistical properties, but the crucial point is they're reducing the size of the expression DAG that we need to sample. They're simplifying the representation and making it faster to evaluate. One particularly emphatic demonstration of this is the central limit theorem, which says that the sum of many different independent samples of the same distribution converges toward a Gaussian distribution. This means that n different samples can be collapsed down to a single sample, meaning that executing this Bayesian network will now be much more efficient. And that's what we're going to do in the next step, which is verification. Taking these Bayesian networks and actually answering the p-assert query. There are two cases you can imagine. First is that sometimes our optimizations are so effective that they collapse down an entire DAG, an entire expression DAG for a program, into a single Bernoulli node. In this case, we can just directly verify whether the probability is greater than the p expressed by the programmer. And this actually happened in a few of our programs. But you might guess this doesn't happen all the time. Our optimizations are far from complete, meaning that most of the time we end up with a probability distribution with a Bayesian network that we can't collapse all the way down. And then we resort to sampling. We execute the Bayesian network many, many times. But now we can use the p and c parameters provided by the programmer to determine the right number of samples to take, so that we can do a successful statistical test, which computes the confidence intervals surrounding the average number of successes and p requested by the programmer, and if they overlap, we say that the verification has succeeded. And if they don't, it doesn't succeed. That's the entire pipeline of p-assert verification. Now I want to talk to you about our implementation that we built of the entire pipeline for the LLVM compiler infrastructure. The pipeline works like this. We take as input a C program, which we ask LLVM to compile down to its intermediate representation, which is a bitcode representation, and then we do our symbolic execution and extract this expression DAG, this Bayesian network, and do some optimizations online and some of them offline to simplify the expression down to something more efficient. I then wrote a compiler pass that can take a Bayesian network and re-emit it as LLVM-IR, which means that we can compile it down to negative code to repeatedly execute it. Aside from all of this, I also built an alternative p-assert verifier that just takes a program and slaps a big for loop around it so that we can repeatedly execute the original code. And I want to emphasize that this strawman, this stress tester that just repeatedly invokes the original program, is a perfectly valid p-assert verifier. It's just really slow because it doesn't take advantage of the distribution extraction or the optimizations on that IR. In order to show the performance contrast, we evaluated a number of benchmarks from the 3 different domains that I introduced at the beginning of the talk. The first is a sensing workload based on GPS, a noisy GPS sensor. The second is that privacy program I showed you at the beginning, where we're averaging the salary from a bunch of users. The first one is a concrete execution of the program where we take a long list of salaries downloaded from a public employee's website. And the second is an abstract version where we give a random distribution capturing the salaries that we expect to see in the wild. The approximate computing benchmarks were taken from previous work on approximate computing, and I want to emphasize here that the task of evaluating how approximation can affect the correctness of an overall program is one of the grand challenges in the domain of approximate computing, and that's what we're trying to address through probabilistic assertions. What I want to show you is the normalized time taken to verify a probabilistic assertion using our verifier. And what you'll see on the x-axis here are all those benchmarks along with the harmonic mean. And on the y-axis, you can see the analysis, the verification time for the tool. And it's normalized to the baseline, to the strawman stress tester I just mentioned, and that's labeled with a B here. And you can see that that all these bars are entirely green, meaning that the normalized time for this baseline is all taken during sampling, the repeated execution of the program. In the following bars, you also see some blue, meaning that we're counting the analysis time as part of the verification for our alternative, for our verifier for probabilistic assertions. First, I want to show you a version of our system that doesn't implement any statistical optimizations. And what you can see is that we already win a lot over the baseline verifier. But you can see for some of the programs we do a lot better, and for some of them we do worse. And in particular, for one of the benchmarks, we actually run a little bit slower than the strawman stress tester. And we can do a lot better if we add on our optimizations that take advantage of the statistical representation. And that's what this bar shows. On average, our verifier is 24 times faster than the naive stress tester. And that most of our time is spent on doing analysis and doing optimization, and sampling goes relatively quickly. And I want to point out that our advantage over the baseline verifier scales with the confidence requested by the programmer. More confidence means more samples. And the sampling time scales with the number of samples we're taking, of course, but the analysis time, the optimization time, stays constant. These results I'm showing you are for a 95% confidence level, meaning about 74,000 samples. If you scale it back to a 90% confidence level, then we take much fewer samples and our advantage decreases, but we're still about 2.5 times faster than the stress tester. Overall, what I want you to take away again is that probabilistic assertions do express really useful properties in modern software, and that our verifier can successfully verify these both efficiently and accurately using a statistical test. Overall, though, I'm really excited about this work because it speaks to a new way of reasoning about probabilistic programs, a type of software that hasn't been particularly well served by verification tools in the past. Thank you.